Hey guys, today we're going to review some concepts that we learned in Algebra 2. We're going to look at parent functions, piecewise functions, and then compositions of functions and inverses of functions. So the first thing we're going to look at is the parent functions handout I gave you. So this handout, front and back, has all of the parent functions that you could possibly need to know for this class, and it also has a lot of information about each of them. So for instance, it gives you the equation, it tells you the name of it, it tells you odd or even, and odd or even just means rotational symmetry. If you haven't talked about that, if it's odd, that means that it has rotational symmetry around the origin. So like if it was in quadrant 1, it would be in quadrant 3 as well, and you could kind of flip it over that line, whereas even functions are symmetric over the y-axis. It also tells you the domain and range and the end behavior of the graph. So the most important thing to know about these graphs are, of course, the equations and the names, and then the picture. The other stuff is just kind of there to help you for other stuff. When you're drawing parent functions, make sure that you list some of those important points out. Like obviously the linear parent function goes through the origin, 1, 1, 2, 2, etc. The absolute value function makes that V shape. Your quadratic parent function is the U shape, which again is just y equals x squared, so you could get your important points there. That should say 1, 1. The square root function, again, it doesn't have any sort of symmetry because it's only in the first quadrant, and there are some of your important points. Cubic and cube root, you've seen a lot. Now, the one thing about exponential and log functions is there's not actually a parent function, but you do need to know the shape of the graph. So if you notice here, they said that the parent function is b to the x. So for this graph, they've actually just graphed, it looks like, 2 to the x. And then over here they did log base 2. So there's not actually a parent function, they just put in numbers to kind of show you what the shape is. You've seen the rational parent function. That's the one that has the two branches and it has those two asymptotes on the x and the y axis. If you take your rational function and you square your denominator, this is what you get. It basically just makes all of your y values positive. So you don't have the branch in the third quadrant, but it's in the second quadrant. The one that you probably haven't ever seen before is the greatest integer function, or a step function. Basically what this does is whatever x you plug in, your y is the integer that it rounds to, basically. So the greatest integer here, if I plugged in x is 2.5, the greatest integer I could get out of that would be 2. And so if I went to x is 2.5 on the graph, which is really tiny, you would see that the y is 2. And so that's basically all it is you plug in a decimal and it gives you the greatest integer you could take out of that function. And you can see the domain and range is kind of funky there. The constant function is, again, that horizontal y equals a number. And then on the back side you have your trig functions. The most important ones that you need to know are sine and cosine, but these other ones might help you for those trig basics quizzes. Here's how you'd find those important points on a sine or cosine graph. You just use your OIO chart, or you think about those important values for pi over 2, pi through pi over 2. And you get these shapes. So you might want to know how to graph all of those parent functions and what their names are. Hint, hint, hint. Now the reason we care about parent functions is so that we can look and graph things like piecewise functions a little bit easier. So a piecewise function is basically just a function that's defined in parts. So they're saying here that my function looks like x plus 2 if x is less than or equal to 0. My function looks like y equals 2 if x is between those two numbers. So when you're graphing a piecewise function, there's two ways to do it. You can make a big old table and just make x and y's and make sure that you include these points that show up with the little like pieces in there. And so if I wanted to pick some values in here, I'd need something less than 0. So maybe I want to do -2 and -1, and I can just plug in those x values into the appropriate equation for it. So -2 plus 2, since this is less than 0, would be 0, and then -1 plus 2 would be 1. And since you notice this one says equal to, I can also graph that 0 with this function, so it would be 2. And so I'd go ahead and just plot those points on my graph, and I put a closed circle right there. And so when I graph those, that just makes that straight line with that y-intercept of 2. And then I go and I figure out some more stuff. So the important part here is that this can't equal to 0. So that means that my closed circle is hanging out right there. That x equals 2 business, or y equals 2, remember, it's just a constant function where everything is equal to 2. And I can have those points up until I get to 4. So 1, 2, 3, 4. And I'm going to put an open circle in there. And that would be that piece of the graph. The last piece of the graph is the square root function. And something to notice here is it also can't equal to 4. So my 4 is going to end up being an open circle no matter what. And so I'm going to plug in some values here. Again, it's the square root of x, so we want to make sure it's something I can actually do. So the square root of 4 would be 2. So it would be here if it could be here. And then the square root of 9 is 3. So I'm going to go out to 9, 4, 5, 6, 8, 9, and that would be up there at 3. And it makes that kind of curvy shape. And that would be the graph of your piecewise function. Looks funky. It will help you in the limits unit. Okay. The next thing we need to talk about is compositions. And compositions are basically when you have two functions and they ask you to find something like this, f of g of 1. So the big deal here is work from the inside out. So start on the inside and then go to the outside, just like that Pixar movie. Okay, so if we have an example, we know f of x is equal to 2x plus 1 and g of x equals x squared. We're going to find g of f of 3. This is just another way to write the composition function. So g of f of 3, these two things are equivalent. So if you see that circle, it just means find the composition. So the first thing I'm going to do is find f of 3. That's the inside. And to find a value of a function, you just plug in for x. So I get 2 times 3 plus 1, which is 7. And then I'm going to take this number and plug it into the second equation. So, and I have this, I'm going to plug it into that whole thing. So I'm going to find g of 7. G of 7 is just 7 squared. So my final answer here would be 49. So it's pretty straightforward when you have numbers. Then, if we look at something like this, we have that f of x equals 1 over x minus 1 and g of x equals x plus 2. First thing that we're going to do is find some of those numerical things. So again, you're always going to start from your inside out. So my g of 1 equals 1 plus 2, or 3. So then I'm going to go ahead and plug that back into the other function. So f of 3 is equal to all of that. And just plug in 3 wherever you see an x, and so that would get me 1/2, and that would be your final answer. Now if I did it the other way and I started with f of 1 first, I'm going to plug in 1 wherever I see an x, and you see here that this would get you 1 over 0. I know I can't divide by 0, so there's really nothing I could plug in there, so my final answer would end right here. It's undefined, it can't go any further, so I move on. Now if they put a variable in here, all that's meaning is that you're going to plug in x or whatever the variable is wherever you see the x in the first equation. So my g of x is x plus 2. So I'm really going to find f of x plus 2. So wherever I see that x in my equation, I'm going to plug in that whole expression. So I'm going to have 1 over, and instead of putting in x, I'm going to put in x plus 2, or that other function value. And oops, sorry, it's minus. Can't read apparently today. And then I just simplify what I can. So that would be x plus 1. And so that would be my final answer there. I simplified as much as I could. If you go the other way, remember f of x is this big thing. So we're finding, use different color, g of 1 over x minus 1. And this can get kind of icky. And I'm just going to go ahead though, wherever I see an x in my f of x, or sorry, g of x equation, I'm going to plug in that whole business. So instead of having an x here, I'm going to have 1 over x minus 1, and then it's plus 2. And I could simplify that down by finding a common denominator, but I know that that's that rational function moved up 2 and to the right 1. That's all you got to do there. Plug in what you know, work from the inside out. The reason that we want to know compositions is so that we can easily prove something is an inverse of something else. So when you're finding an inverse, all you have to do is switch your x and y and then solve for y. And so I'm going to go ahead, if I'm finding the inverse of y equals 1/2 x cubed minus 4, Wherever I see a y, I'm going to put an x, and wherever I see an x, I'm going to put a y. And then I'm just going to try to solve this and get y by itself. So then I could look in my calculator if I wanted to find specific values. Be careful in this next part. You're going to multiply by 2 to get rid of that 1/2, but you've got to multiply everything over on the left side by that 2. And then in order to get rid of a cube, you're going to take the cube root. So I find that the inverse of this is the cube root of 2x plus 8. Now the way that we can write that is instead of just writing y equals, we write f to the negative 1 of x, especially if it had been f of x to start with. So that implies that you are looking at the inverse function. So my inverse function for this guy is 2x, or a cube root of 2x plus 8. Now here's a really easy way to tell if the two things are inverses. So if they give you two equations and they say, is this one an inverse of the other one, you're going to find f of g of x, it better equal what g of f of x is, and that's actually going to give you x. So if I tested this out and I wanted to find f of g of x, and we'll call my inverse g of x, and this one f of x, if I find that, that means I'm just plugging in this entire thing into my first equation. So I'd have 1/2 times the cube root of 2x plus 8, all cubed, minus 4. And so then I just simplify this out. I get 1/2. If I cube a cube root, it just gives me whatever was inside the radical. And then I simplify. So I get that that's 1x plus 4 minus 4. 4's cancel, and I get x. So that's a way that I can prove it. And then of course you're going to want to try g of f of x, and we'd see that we get the same thing, because if I take the cube root of a cube, that would also cancel out the function and would just leave me with x. So that's the way to prove that something is an inverse. Now when you're an inverse of a function, remember that just flips you around, it reflects you over that line y equals x. So if I was to graph these, my two things would be, if I have a cube function, it would look kind of like this, and then my cube root function would be reflected over that axis, and that looks terrible. Kind of looks like some DNA apparently. So again, it's reflected. You're just switching your x's and your y's. And something else that you may have seen or you may not have seen are called one-to-one functions. Now, when a one-to-one function, all that means is that the inverse is also a function. So a one-to-one means that your inverse is also a function. Every y has exactly one x. So you know that a function, every x has one y. This just goes the opposite way, and you have the horizontal line test. So if I looked at something that was not one-to-one, the function y equals x squared is not one-to-one because it doesn't pass that horizontal line test. And I would know if I tried to flip that over the line y equals x, it would look like this, and that guy's not a function. Whereas if you had something like the rational function, every y only has one x, it passes the horizontal line test, and then when I flipped it over, it would actually do the same thing, but it would be a function. So that's the purpose of knowing how to find an inverse. Okay, and that's all I got. Again, make sure you know all those parent functions, and I will see you tomorrow.